Hello and welcome to Physics 2212 Lab 6 Faraday's Law. The goal of this lab was to analyze the dynamics of a magnet falling through a conducting aluminum tube. This was then compared to the dynamical results obtained from a computational model. And for a brief preview of the results, the average time to fall was 0.436 seconds. The computed time to fall, however, was 0.374 seconds. Starting off with some key principles, the potential difference is given by the negative change in the magnetic flux with respect to time. Here, the magnetic flux is given by integrating over the entire area A using the dot product between the magnetic field and the area vector. And finally, the change in flux through the tube can be given by the formula at the bottom. Also, the magnetic force on a current carrying wire is given by the current I times L cross B. Ohm's law states that the current is given by dividing the voltage by the resistance. For the experimental procedure, the dimensions of the tube were measured. Next, the mass of the magnet was measured as well. The magnet was then dropped from rest down the tube and the time taken for it to fall through was measured. And finally, step 3 was repeated 5 times before the average of the times was taken. Here are the results from the experiment. When averaged, it gives a time of 0.436 seconds for the magnet to fall down the tube from rest. And for the computational model, here is a diagram. Here the magnet was dropped with the north pole facing downward, and by Lenz's law, the current should flow in the loop such as to oppose the change in magnetic flux from the falling magnet. We modeled the conducting tube as a series of conducting rings stacked on top of one another. Here, our system is the falling magnet. Surroundings consist of the aluminum foil tube and the earth. For the code, we first established the initial parameters of the simulation, such as the length of the tube and radius of our conducting rings. Here, we also established other parameters of the simulation. Next, we defined our dipole calculation function here, and then we calculated change in magnetic flux in this function. For the actual simulation loop, we established the force due to gravity to be mass times gravity. Next, the current is given by dividing the EMF by the resistance of each conducting ring. Here we calculated the magnetic force on each ring due to the magnetic dipole. Then, using Newton's third law, we are then able to recognize the force of the magnet is simply the same magnitude as that acting on the ring, but just in a different direction. Next, we calculate the net force to be the sum of the gravitational and magnetic force. Then we simply update the position and velocity of our bar magnet. Here, the computational results show that it takes 0.374 seconds for the magnet to fall through. When the magnetic dipole was flipped, we still achieved the same velocity time graph, except the direction of flow of the current was different. Here, the magnet slowed down, approaching a terminal velocity before falling completely through the tube. Ultimately, the computational model predicted a time of 0.374 seconds, whilst experimental results showed an average of 0.436 seconds. Possible sources of error include contact/friction between the magnet and the tube, causing it to take slower to reach the bottom of the tube. Also, the dipole moment may have been wrong from previous results, which would have led to a discrepancy between the computational model and experimental results. There may have also been random error with timing and air resistance, which would have led to some error. Finally, if the resistivity of the conductor were reduced as close as possible to zero, according to Ohm's law, this would lead to a greater current being produced. This would ultimately lead to a greater magnetic force to act on the magnet. Therefore, the magnet will reach terminal velocity quicker, leading it to fall slower as well. And finally, if holes or slots were cut into the tube, this would disrupt the formation of ring currents, which would lead to less magnetic force opposing the dipole. This would lead to the magnet falling quicker.